everyone, this is Sukesh Kulkarni. How are you? Hope you're doing well and welcome to my channel Cosmic Science. In previous video, we have discussed about work done under constant force. Work is done where force was constant. Here today we'll be learning work done by varying force. What does that mean? Let's see. Work done by varying force. Done by varying force. Suppose there is an object here. For example, a train. A train's engine is moving, applying force and pulling the other bogies of the train. So it's applying the force in a particular direction. But how does it apply? It's not constant all the time, right? It applies wherever the crossing is there, then it slows down, and again when it is normal track, it will move fast. So there is a variation of force applied by the engine to the bogies. In the same way, uh, work done by a very variable force, and also in the same way the displacement also will uh, be varied. So let's see uh, what does this exact sentence mean. Consider a um, consider a varying force acting on a particular body, and the displacement is in the direction of the force applied. Okay, so this is a basic definition. Let's see how to visualize this definition: the varying force acting on a body and the displacement. How can it correlate these all the terms? Let's see through a graph. So starting point is here. It starts like this. Its force increases and becomes like this. This is force. This is f of x force, and this is a displacement. This is a force. This is a force, and this is displacement. Force increases, displacement also increases. It increases, and here it is in this way. So this is the visualization of variation of force uh, and of variation of displacement, and we need to calculate total work done by these variations of force and displacement, right? So firstly, we need to divide. So if you want to find this uh, displacement and force curve, we need to divide this areas, into small areas. Why? Because we can't find the direct force and the displacement from this. We need to take small parts to calculate uh, the displacement and force, and calculating these uh, small parts, we can calculate, we can sum up all those things, and then we calculate total work done. So this area is delta x. This area is delta x, a small region. This is delta x. It is so small that force remains constant over all this interval. This is over starting xi, and this is xf. From xi to xf, the force remains constant over small intervals, not whole. If you take this, your force is constant. If you take this one, force remains constant, because there is small difference in the force. So therefore the force remains constant. So we need to calculate right now is total work done, right? We have divided this, and and we will sum up all the divisions, and we will calculate work, total work done. So work done is given by delta W f of x into delta x. So here we need to apply summation. We have to add all these displacement and force. So we need summation of this. Total work done is a summation of xi to xf. From xi to xf, we do it, take it, and summation of delta w. So what will be the this value? It will be this. W is equal to xi to xf. What is delta w? F of x into delta x. F of x into delta x. So now, uh, suppose, uh, delta x value displacement increases or decreases to zero. If the displacement is zero, even the force is acting, acting, but displacement is zero, then the lines will come like this, closer and closer and closer. There are small displacements which can be neglected. So we can say uh, the value is finite. So we get a finite value. So we can take a limit del, limit delta x tends to 0, xi xf f of x dot delta x. So we have taken limit that it is tending to 0, because if it becomes 0, it is near to 0, it will become a finite value, right? So this is why we are taking a limit tool. So further we integrated integration of xi to xf f of x delta x. So why did we change from a summation to integration? Summation will give you sum of all of this, and integration will give you whole region. This whole region, this this integration will give you whole region around this curve, below this curve. So that is the reason we take integration of the f of x into delta x. So this is the final answer. This is a total work done by a varying force, and a varying displacement. So this was about work done by variable force. We'll see work done. We'll see work energy theorem. Let's see that. Work energy theorem. What does this mean? Work energy theorem. What does this mean? It says that how work is related to the energy. It gives an equation for work, how it is related to energy. We'll calculate that. Let's get started. Work energy theorem. Work energy theorem. Consider a equation of kinetic energy. K is equal to half mv square. If we differentiate this with respect to t, we get dk by dt half m. M is constant. We differentiate v square 2v dv by dt. This two get cancelled. What remains? dk into dt divided by dt, m into v, m v dv by dt. So dk by dt, what is m into dv by dt? What is dv by dt? Acceleration, right? So this becomes ma. We can write it as force into velocity. So we take this dt in this side. Dk is equal to f v into dt. Now what can we do? We need a relation between for work done and work done and energy. This kinetic energy and work done. We need to calculate. So we integrate it from xi to xf, ki to kf into dk, xi to xf, f into v dt. What is v here? What is v? What is v here? Dx by dt here into dt. This dt will get cancelled. It remains as it gives the value k is equal to uh, dx is the right force into displacement. If we take this one on here, we get xi to xf, f into dx. This equal to ki to kf into dk. So what is integration of x1 xi to xf into force dot dx? What is force into displacement? Work done. This gives you total work done, right? We have seen in the earlier uh, work done by variable force. We have seen integration of xi to xf, f dot dx is nothing but total work done. Work done is nothing but this is k here, k integration xi, sorry, ki to kf. Work done is equal to how do we solve this? Upper limit minus lower limit. Kf minus ki. So this is work energy theorem. This equation shows total work done is equal to uh, final kinetic energy minus initial kinetic energy. This is here kinetic energy is varying due to the force is varying. So total work done will be final kinetic energy and initial kinetic energy. This is the work energy theorem, and this is the explanation for W is equal to Kf minus Ki. So this is a work energy theorem. So total work done is K final final kinetic energy minus initial kinetic energy. So it's the difference between these energies from initial to final we have seen in the graph. Initial to final we have seen from here. Initial to final here total uh, from here to here Ki to Kf. We minus Kf and 2 Ki total kinetic energy. This will give you is equal to total work done. This was about work done by variable force and work energy theorem. So if you like it, if you have understood, if you have any doubts, comment down below. And if you really like it, if you like the um, if you like the explanation and the presentation, please do like and share as much as possible, um, so that other people can watch this session or watch my lecture. With this, we'll take your leave. See you in the next video. Till then, stay safe, stay healthy, stay calm, and stay motivated. Thank you.